Okay, so let's see. We talked. What did we leave off yesterday? I can't remember. Did we get? No, we didn't get there. Okay, so we were just talking about about units, about base units and derived units. Okay, so yeah, when we want to do physics, we work with real quantities, and so we're concerned with units. I think we were just talking about really the top three for a long time is those are our base units, and then we'll look at lots of derived units that are built from those. Just as an example, let's look at just one. Soon we'll be talking about force, and in force, the units in terms of base units, units of force are kilograms times meters per second squared, or kilogram meters per second squared. But that's kind of a mouthful, and we use force a lot, and so we actually give force its own units. We're going to come to see that the standard unit of force is the Newton, but just know that a Newton is actually built from the MKS base units, right? They all will be. Okay? Questions? That make sense? So there they are. They're in your book also. What happens though when we want to talk about very widely varying scales in physics, and we want to deal, we still want to talk about quantities, but if we're talking about the mass of an electron compared to the mass of a galaxy, those are pretty far apart, and so frequently we will, we'll use SI prefixes, right, to make the units, the scale of the units much bigger or smaller. I think in our book, I think it only maybe goes up through tera, which is pretty big, and then down through femto. But there are others. I don't know what they are. I mean, you couldn't have, if you asked me what 10 to the 24 was, I wouldn't have known. I would just Google it. But we don't, you'll see these sometimes. Like a nanometer is one that if you're talking about atomic scale stuff, yeah, if you're talking about a nanometer scale, you're starting to get down almost to the scale of atoms. That's where we can actually start to do some engineering on that scale, like of semiconductor fabrication and things. It gets down to approaching like the nanometer scale. So anyway, you don't have to write that down by any means. It's in your book. Not a big deal. Just want to make you aware. You've seen these before, but these are the prefixes that go with the various powers of 10 that we adhere to our base units. Like if we talk about, for example, a megameter, what is it? Yeah, 10 is that many meters, so it's 1,000,000 meters, 10 to the 6 meters, right? If we talk about a micrometer, we're talking about 1/1,000,000th of a meter, right? Okay, so on and so forth. All right, so we sometimes, as I mentioned, run into some issues of scale. If we want to talk about the electron mass, for example, that's an inconvenient number to write, isn't it? Right? If we want to talk about the mass of the Earth, I didn't put the units up there for this, but it's kilograms. That's also an inconvenient. If we want to talk about the number of atoms in the observable universe, that's a really inconvenient number to write. So how do we deal with that? Let's say we want to retain units of the standard units like kilograms. Okay, yeah, we have to have a different approach to writing these big numbers. And the approach we take, you've dealt with this before in your science and chemistry classes, is scientific notation. So let's just kind of review the rules of scientific notation. When we write numbers in scientific notation, we want them to look like some number. I'm just going to call it, let's call it A times 10 to the n. That's the model that we want to fit, right? They all kind of look like that. What are the criteria that would make this a legitimate, we have to kind of check off, that would make this a legitimate scientific notation number? What are the values that A could have? And then think about this for a second. Maybe even just turn to your neighbor and review this. And be careful with this one. Okay, so say that again. So A should have one number to the left of the decimal. Okay, what could that number be? A 0? Okay, so it's got to be a number. Okay, good. Then that's probably the best way to think about it. The number has to be greater than or equal to 1 and less than 10. Does that make sense? So A must be greater than or equal to 1 and less than 10. Very good. Okay. What about N? Could be any. Okay, well, okay, it's any real number, so it could be like pi.
Well, no.
Okay, so it has to be a whole number. Okay, so whole number would be the set of 0 through 1, 2, 3, 4, etc. Can't be 0 here.
Yeah, right. Can it not be 0? Well, doesn't
Yeah.
that just be 1?
Okay, so what if we took, let's take an example. What if we have something like 3.1 times 10 to the 0? That's the same thing as saying 3.1 times 1, right? Okay, so technically, that's okay. I get your point, maybe. It's just not very useful, right? But it does work, right? It does work. It actually is. It could be 0. We just choose not to use that value very often, but we're still missing something. Could be negative too, right? So it's not just whole numbers. It's actually, what would that set be called? Say it again. Integers. Yeah. So N would have to be an element of the set of integers, okay? Which is sometimes written as a capital I, usually as a capital J, okay? And we know what integers are. Those are, the way I like to describe them, those are just all the hash marks on a number line, right? So if we look at the real line, and that's 0, and that's -1, and that's -2, and that process continues forever. It's just each of the hash marks in an integer, right? Okay, good. So let's take, for example, the electron mass up here, and let's rewrite that using scientific notation.
Could you even be able to say the bottom number? Like, is there even a word to
Not that I know of,
Yeah.
yeah. I mean, maybe there is. It'd be kind of, that'd be like some arcane trivia, though. No one would ever use that, yeah.
Is that like the rough estimate?
Yeah, it's an estimate, yeah. An estimate of the number of atoms in the observable universe, yeah. So the electron mass, I did try to group this in packets of 3 so you could see. So what's this going to be then? We got to move the decimal over 3, 6, 9, 12, 15, 18, 21, 24, 27, 31, right? Okay. So we get 9.11 times 10 to the, okay, negative, right? How come? Okay, we're moving it right. In other words, because the decimal is, what we really probably want to think about is, how far did we have to move it from 9.11? We had to move it left to get there, right? Either way you think about it, if the decimal starts off to the left of our first digit, that means it's a negative scientific notation. Or if you prefer to think of it as, I have to move the decimal to the right to turn it into scientific notation. Or this number is less than 1. Any of those, they're all consistent with each other. So this is times 10 to the -31 kilograms. Go ahead.
1 trendecillion.
Wow.
Trendecillion?
Trendecillion.
There you go. Okay, well that's good to know. Trendecillion. So the mass of the Earth, if I wrote this out correctly, should have been 5.98 times 10 to the 24. Positive this time though, right? Because this time the decimal starts there, and I've got to move it left, right, to get scientific notation, to get my value, what we call the A, right? The number to be greater than 1, greater than or equal to 1 and less than 10. Another way of thinking of it is this number is clearly bigger than 1. Yeah, okay. So 5.98 times 10 to the 24 kilograms. And I don't know if I did this right or not. You can count, but it should be about 10 to the 80. Okay, so if I write that, it's an interesting point there. If I write that as 10 to the 80, is that scientific notation? Well, I mean, arguably, I kind of was lazy about it, but if I were to write it maybe specifically or exactly as scientific notation, what would I have to add? Yeah, 1 times.
But technically that is right. 10 to the.
I would say, yeah, to me, I would say I consider that scientific notation. Yeah, the ones just kind of apply. Yes, sir.
Oh wait, never mind. You're just multiplying by ones.
Yeah,
Never mind.
so it's a 1 followed by 80 zeros. Okay?
Or to just say.
Okay, what's,
That's the easiest.
what's the biggest number, well, we're just having fun here, what's the biggest number you know? Google.
Google, yeah.
Okay, what is a Google?
I don't know, it says
100 zeros?
Yeah, it's 10 to the 100. Yeah, that's what it is. 10 to the 100. And by the way, Google is spelled wrong. Google is spelled wrong. I mean, I'm sure they meant to do this. They're pretty smart people. But when you Google something, the name of that company, I assume, is loosely based on, or maybe not so loosely based on, the number Google. But when you spell a Google, that's how you spell a Google. A Google is equal to 10 to the 100. That's huge.
I'm pretty sure they spelled it like that. So you know how they change it?
Oh, they did spell like that one day?
I think so.
Yeah, I think I saw that.
Because that, yeah.
I think I saw that. It was on some day where it made sense too. I
Right.
remember that. So that's a big number, right? That's bigger than the number of elementary particles in the universe. So that's obviously a pretty huge number.
Isn't it Googleplex?
Okay, so you know what a Googleplex is?
What's the 200?
A Googleplex is 10 to the Google power. In other words, it's 10 to the 10 to the 100. So to write a Googleplex, it's a 1 followed by a Google number of zeros, which is, so even just writing it wouldn't fit in the universe. But yeah,
You can never write that.
no, you couldn't write it. Couldn't write it. Even if you put 1 0 on every subatomic particle in the universe, you still couldn't write it, and we can't write that font. You know what I mean? So there's no way you could possibly write it. Yes.
Is there a name for like everything in between 1 and Google?
No. Does everything get a special name? No. No, Google gets a special name just because it's such a, 10 to the 100. That's a pretty round number, so to speak. Yeah.
Wait,
Okay.
so a Googleplex is only just 1 0?
No, a Googleplex is 1 followed by Google zeros.
But okay.
What do you suppose a Googleplex is?
A lot.
Put another 10 down below.
Exactly. Another 10. It's 10 to the Googleplex power. Yeah, and you could go on and on. Okay. So we'll come back to this screen here in just a little bit, but there's our quick review of scientific notation. Actually, we're not quite done. We also need, did I make a screen for this? Oh, well, I did that. Okay, so how'd you do something like this? I'm just gonna throw something out there, see how we deal with it. What if we wanted to do 1.23 times 10 to the 5th, that's a 5, plus 2.31 times 10 to the 5th.
Put it in a
Times the
calculator.
number sealed and then add the exponents.
Say it again.
Times the number sealed and then add
Okay, now I'm adding. Okay, there you go. Right. So now that's gonna make it different. Yeah, you were on the right track. What are we gonna do?
the. Just add.
I can't remember if the book talks about this or not, but you guys have done this before. But so short answer is you can always just enter these numbers on your calculator, which 99 times out of 100 you're going to do. But there's some good number sense issues that come up here. When we multiply, I'm going to give you just sort of a subtle hint of sorts, and then you're going to give me the answer. When I multiply things, I'm really talking about groups, aren't I? Like if and these really are, when I write something in scientific notation, this product isn't just in name, it really is a product, right? It's the number 1.23 times the number 10 to the 5, right? If I have 6 times 8, for example, isn't that just we could think of that as being 6 groups of 8, right? Or 8 groups of 6, but for our purposes, let's think of it as being 6 groups of 8. So
So we-
I've got 1.23 groups of 10 to the 5th plus 2.3 groups of 10 to the 5th. Now, if I have 6 marbles plus 8 marbles, how many marbles do I have?
Oh, you have to find the differences.
Well, what you just
Yeah,
add the.
you add them.
You
add the
know,
numbers
exactly,
and
right.
find the difference between the exponents since they're the same.
No, you
So you
don't.
just add the two numbers,
But-
leave the
But what,
exponents,
in,
'cause-
Yeah, yeah.
no,
Right.
in the event of
If
the
they
exponents
were-
being different,
Oh.
That's what
then
I'm
you
saying.
can find the
You're right,
difference in this
you're right.
case.
Okay, but let's see if everybody, here's maybe a way to think about that. Would you agree, I mean, I don't mean to insult you here, but this is a good way to think about it. If I have 6 marbles plus 8 marbles is obviously 14 marbles, right? Shouldn't that also apply to bags of marbles, right? If I have 6 bags of marbles and 8 bags of marbles, I have 14 bags of marbles. Well, what if my bags of marbles each have 10 to the 5 marbles in them?
That's
Then I've just
a lot of
got
marbles.
14 bags with that many
Yeah.
bags of 10 to the 5th marbles, right?
Right.
See what I'm saying? So really, this is, you can almost think of this like a variable in a way, right? And you can. If we were gonna do something like whoops, let me color code this a little bit. Try to do this as much as I can. 1.23, call it x, well, x is confusing, let's make it y, plus 2.31 y. You would all know how to deal with that, we're just adding like terms, right? Everybody agree?
Yeah.
This is just gonna be, you tell me, what's it gonna be, what, 3.54, did I do that right? 3.54y, right? Same thing here, right? These are just, I have 1.23 groups of y plus 2.31 instances of y, maybe I should say. So I have that many total. So what's my answer up here? Yeah, I just get 3.54 times this common factor. That's all the y is a common factor, right? Okay. Or group, or groups of marbles or whatever we're counting, right? Okay. All right, so how would my thinking change if I'm going to change this very slightly here? What if we wanted to do something like 1.23 times 10 to the 5th plus 2.31 times 10 to the 6th. I don't say anything out loud, just stare at that for a second, and I'll give you permission to talk to your neighbor about it if you want to. That's fine. Can I just add, can I do the same kind of thinking on this one? Not directly, obviously, can I? Because I've got different groups. I've got 1.23 groups of this many plus 2.31 groups of that many. Well, those aren't like terms anymore, are they?
Right. We could just want to make them like terms.
Okay.
Won't make it improper.
Okay, so
Maybe that's
suggestions.
Yeah.
What do you think? Suggestions here.
Would it be improper to just, move, like, for example, on the 2.31, make it, 23.1 times 10 to the 5th,
Okay,
and then just.
What do you think?
And correct that when you have the
Wait, that
numbers.
one?
does that make sense? Okay, does everybody see that? Scott, you want to add
I
something?
was just thinking, could we do it the other way, make 1.23, make it 0.0123,
Sure.
and then we don't have to convert it back, it's just add it in.
Yeah, that's fine. And maybe I see, I can actually, yeah, that's fine. That's good thinking. Either one of those really would be okay, right? But in order to get there, do you see right here now, if this is 2.31 times 10 to the 6th, if I want to write this, just for example, in terms of 10 to the 5th, what am I effectively doing? If I rewrite this in terms of 10 to the 5th, the whole number, this complete number has to have the same magnitude before and after, right? The amount, the quantity can't change. So whatever I do to this factor, I must do the opposite to this factor, or the inverse to that factor. Does that make sense? Okay. So what am I doing when I convert this from 10 to the 6th to 10 to the 5th?
Making it small. Making it small.
Okay, I'm dividing it by 10 to the 1, aren't I? That make sense? So if I'm gonna divide this one by, really all I can do here is I can multiply this whole thing by 10 over 10 is a way of thinking about it, right? I'm gonna take the bottom 10 and group it with this factor, agreed? So it's the same thing as saying 2.31 times 10 to the 6, and I'm gonna take this bottom one and stick that one there, right? The top one is gonna get attached to the first factor. I still just multiplied by 10 over 10, which is 1, right? And that's our multiplicative identity. Or, that's a mouthful, but our identity number for multiplication, right? That's the one special number we can multiply by and preserve identity, right? And so what's the outcome gonna be then? This number becomes 23.1, and this one becomes 10 to the 6 over 10 to the 1. Well, we know how to do this, right? This is really just a property of exponents.
Right.
If I divide like bases, what do I do to the exponents? Subtract. Right? And so I can rewrite this number as 23.1 times 10 to the 5th, right? Now, what's a shortcut? There's kind of the theory behind it, but what's our shortcut? Yeah, good. If I'm going to reduce the power of 10 by 1, that means I have to move the decimal to the right by 1 over here. Agreed? Okay, so one way we could look at this is 1.23 times 10 to the 5th plus 23.1 times 10 to the 5th. And now these are like terms, right? We have groups of like factors that we can add up. Agreed? Okay, the other way, good suggestion. Scott said, well, we're going to leave this probably in terms of, if we add this thing up, let's just do this math real quick because I want to make this point. This was really good thinking.
It's going to be 2.3223 times 10 to the 6.
So it's going to be, right, so if we leave it in terms of 10 to the 5th, I'm going to get 24.33. Everybody agree?
Yeah.
Okay. Times 10 to the 5th. Is that an appropriate way to leave that, though, for scientific notation? What rule am I breaking?
One number to the left.
Oh, okay, yeah, that's not less than 10, is it? So I've got to make a conversion here. I've got to move the decimal one place to the left. So if this number's getting smaller by a factor of 10, that one's got to get bigger, right? So our answer is 2.433 times 10 to the 6. What Scott saw, which is really clever, was we could, instead of doing what we did here, why don't we just anticipate that we're going to, being as this number is already on the order of magnitude of 10 to the 6, right? So that this one's going to be just a little smidge, a 0.123 times 10 to the 6. Why not change this one and then add them, and then we'll get this answer directly. Everybody see that? I thought that was kind of cool. Okay. All right. What about, let's shift gears here. What about, oops, not quite there yet. What about multiplying scientific notation? So what if we want to do something like 1.23 times 10 to the 5th times 2.31 times 10 to the 5th. Now just think about that for a second. Did I mess that up? No. I'm going to write it like this for a second, just to make this. Okay. Don't say anything. Just think about that a little bit. Any ideas? Brianna, did I say that right? What do you think? Not sure? We got a pretty good idea maybe how to do this? And I want more than that, I want an explanation of maybe why too. Okay. Kate, what do you think?
Multiply the main numbers and then add the exponents.
Okay. Suggestion is you're going to multiply the coefficients,
Okay.
right?
Yeah.
And then you're going to keep the base 10 but add the exponents. Okay, that's correct. How come though? Let's see why. Let me ask you something. What is, be a way to, I think this will illustrate this pretty well. Let's try this. What is 2 times 3 times 4? Everybody, what is that? 24, right? What if I add times 5? It's just, what, 120 maybe, right? Okay, everybody agree? And maybe you got that by taking 24 times 5, but if you were just starting from scratch with this one, and there's a lot of good stuff going on here, so really focus in on this. How might I do that product if I were starting from scratch to make it easier?
2 times 3.
Okay, you could do 2 times 3 times 4 times 5, or I'd say maybe there's even an easier way.
5 times 2.
No? 5
5 times 2.
times 2, why not, right? If you can multiply by 10 is the easiest thing in the world. That's just a matter of moving the decimal, right? So if we wanted to, we could make this equal to 2 times 5 times 3 times 4, right? I know this is just, I'm sure you're thinking, why do this is arithmetic, but there's something pretty cool going on here that's going to illustrate why we do this the way we do. So 2 times 5 is 10, 3 times 4 is 12. Well, 12 times 10 just add a 0, right? So it's 120, okay? What justifies our being able to do that? Remember the properties of equality? Okay, say it again. No, not identity.
Cosine.
What did we do? We switched around the order, didn't we? Okay, so what's the property of multiplication that allows us to flip around however we want to? Do you remember?
Middle school stuff.
It is middle school stuff. Not that this is critical for this class at all, but I'm just going to take an opportunity to hit this up so you'll remember it next time. No,
Does it start with C?
no, it doesn't.
Reason 8.
It's the, oh, okay, I'm sorry, yeah, you did. We're doing the flip one, yeah. It's the commutative property, right? The way you can remember that, just as somebody who's taught lots of algebra, the way I tell people to remember that is, you commute to work and then you commute back home, right? So you're just changing your places during the day when you commute. So that property is going to allow us to, the commutative property allows us to commute or exchange factors, right? The other thing we did though is we chose the order in which we added these. Something I really want to point out that people oftentimes forget is that we always multiply factors in pairs. Okay? I don't know how many times I've seen situations like where we're multiplying, something like 2 times the quantity xy. And I oftentimes see people doing things like this. They're going to go 2x times 2y equals 4xy, which isn't right, is it? Because we double multiply. We always multiply things in pairs. And so when you told me the answer was 24, you were correct because you did one of two things. I'll just do one of them. You may have said 2 times 3 is 6 times 4, right? But what you did not do is say 2 times 3 times 2 times 4. That would be incorrect. Everybody agree? You have to multiply only in pairs. You could say 2 times 3 is 6. There was a pair that I multiplied, and then I take that 6 and I multiply by 4. There's another pair that I multiply, correct? What we did here is we grouped the pairs that we multiplied, so we multiplied them in an order that made the problem simpler, right? What's that property called? It allows us to group the product pairs in any order that we want to when we're multiplying. Commutative lets us mix them around. You choose who you associate with, don't you? Oh, there's associative property, okay. So you choose your group, you choose your associates, right? So this is the associative property, okay? So how now can we, given the fact that we can do this kind of stuff, how many factors are there in this product up here? Exactly how many factors are there? There are 4. What are they?
Coefficients.
1.23 times 10 to the 5th times 2.31 times 10 to the 5th, right? So let's group those in any way we want to. We have to multiply them in pairs, but let's group them. Well, what you were telling me to do without maybe thinking, what the logic behind it was, just because you've done this a lot and it made sense to you, which is good. You were doing something like this, weren't you? Weren't you saying 1.23 times 2.31 times 10 to the 5th times 10 to the 5th. And it's uncomfortable for me to make that cross. It's just, we don't want to do that, do we? Because it looks like an X, but I did it. Shows up in scientific notation, right? So this answer is something. I don't know. What is it, somebody? Somebody on your calculator. I don't feel like doing this.
2.8413.
Okay. Times, well, when we multiply like bases, what do we do to the exponents? We add the exponents, sure. So it's times 10 to the 10th, right? Make sense? All right. Okay. What would we do? Say we had something like, and it wouldn't have been a big deal here. Let me just, before I move on. Last time it caused us, we had to ponder this a little bit, but this time if that had been a 10 to the 6, big deal. What difference does it make, right? All that's going to do is make this a 6, and so what do we end up getting for our exponent? 11, yeah. Right? No big. Okay, how about this one? What if we have something like 1.23 times 10 to the 5th divided by 2.31 times 10 to the 6th. Are we probably going to group that one? Same kind of thing, isn't it? Yeah, we're really just going to think about this as a product of those two quotients, aren't we? Right? We're going to get a decimal answer here, which is what? It's probably repeating.
0.532.
0.532.
I could go
You
on
can
if
keep
you
going,
want.
so we'll just call it 0.5328.
4.
Oh,
I mean,
4.
if you want to do 8.
Okay.
We'll
We'll do it correctly. I think that's embarrassing. I don't think I've ever done that before.
That's not good.
Oh my God. Please don't tell anybody. That's pretty bad. Oh my gosh. That's kind of embarrassing. Times, yeah, so what's this one gonna be? So if I divide like bases, I subtract, right? So it's times 10 to the negative 1, right? 5 minus 6. Okay, and what would I have to do here to make this? That doesn't quite work, does it? Yeah, I got to move the decimal, don't I? So if I move the decimal to the right by 1, I am increasing this number by a factor of 10. So what do I have to do here?
Decrease that.
Decrease it. Good. So I got to subtract 1, which makes it a negative 2, right? So my answer ends up being roughly 5.324 times 10 to the minus 2, right? Okay. So even if you didn't have a fancy scientific calculator with you that did scientific notation, we could still do it, right? Okay. Good. Good. Questions? Okay. Moving on. Converting units. You've done a ton of this, but let's just, because it's the beginning of the year and your brains have been a little stagnant here maybe over the summer, let's just review this. Humor me and let's just review this a little bit. So we're going to use, technically what's called the factor label method. It's what I've always just called changer, using changers. So let's take something like, for example, let's convert, okay, let's start easy here. Let's convert 1.24 grams to kilograms, right? So when we use the factor label method or the changer method, here's how we do this. 1.24 kilograms times something is going to equal some number of kilograms. Oops, grams. Oh, hang on, I got it backwards. Should I go ahead and erase this one again? That's supposed to be grams. Isn't it? Okay, so talk to me about this. What do we do?
Count. Count the number of kilograms.
Okay, and so, that's kind of what I expected maybe you do, is you just, there's an easy conversion, and so you just think of what that number is and you multiply by the number. Okay. That can get a little bit complicated, however, when you have more complicated quantities to change. Quantities that maybe are like rates, for example. Okay, so I'm going to remind you about a way to do this that will always work. It's easy to keep track of, guaranteed to get a right answer. You can kind of rest your brain on this one and just follow the procedure. So we know that I'm going to multiply by a factor. The value of that factor in terms of units has to be what? Well, okay, but if I want, let me say this a different way. That was really convoluted. So I've got some number of grams and I want to get some number of kilograms. Those are masses, right? But the ending mass and the starting mass have to be the same, don't they? Right? So what's it going to be?
That's gonna have to be 1.
Yeah, this has to, you're right, this has to be 1, right? Because I'm multiplying by a factor, and we already said the identity number for multiplication is 1. I don't want to change the amount, I just want to change the form. So keep going.
So it's just 1 gram. The grams can cancel.
Good, okay, good. So and that's a very good point. That's what I was going to say, I'm glad you said that, is that the units, I would always start with the units, right? Because you want to end up with kilograms, and to get there, you got to cancel the grams, right? So we know right away a gram has to go on the bottom because I need to do this, right? The unit that I want to end up with is a kilogram, so I know that a kilogram has to go on top. Now I just have to have a factor with a value of 1, right? That's going to have kilograms on the top and grams on the bottom. So all I have to do is think about an equivalent number of kilograms and grams, and almost always we'll just take one of the big unit and ask how many of the little units build that, right? So kilograms are bigger.
Isn't it 1/1,000?
Yeah, kilo means 1,000, right? So there's 1,000 grams in a kilogram, and so that's it, right? So we get 1.24 divided by 1,000. Dividing by 1,000 is like multiplying or moving the decimal 1, 2, 3 places, right? So it's 0. What is that going to be? 0, 1. Oops, 001. 00124 kilograms, right? Would you agree? If I just do the math, so to speak, I'm going to multiply straight across, so I get 1.24 is the number on the top. There's really a 1 there, right? 1 times 1,000 is 1,000 on the bottom, okay? And so if that's the numerical part, the units, we're left with kilograms, okay? Let's look at one that's just a little bit harder. And you'll see why this technique is maybe useful here. So say we want to convert 70 miles per hour to meters per second. If all you can remember is that 1 inch equals 2.54 centimeters. And I always find myself in these situations where I only remember like one of the conversions that I need, and maybe it's not the convenient one, but that's all right. It works. So we're going to start with, 70 miles per hour. So there's an implied 1 there, right? And we want to get all the way over to meters per second, right? So let's multiply by a changer. Well, which one do you want to change first? Miles? Okay, we'll go miles. So we want to get from miles to centimeters, and the place where we're going to go from conventional to metric is 1 inch equals 2.54 centimeters. So this could be a long path, but that's all right. We're just going to multiply by a series of changers. We got to get from miles to inches, and then we can go from inches to centimeters, right? Does that make sense? Okay. So what do you know about a mile? Okay, what is it? 5,280 feet. There's one we probably know, right? So 1 mile, we're gonna go from miles to feet. So miles have to go on the bottom, because those have to cancel, right? We're gonna go from miles to feet. So 1 mile is 5,280 feet. So far, so good. We're closer. Now we can go from feet to inches, right? So we'll multiply by another changer. So now this time we want the feet to cancel. And we want to get inches, correct? So 1 foot, we all know, is 12 inches. Okay, and we're partway there. Voila, we've got inches. Do we want inches? Yeah. We're trying to write this in terms of, oh, no, we're not, okay, we're not there, sorry. We're not close to it. But now we have a conversion where we can go to centimeters, right? So we could go inches canceling in favor of centimeters, right? And here's our conversion. 1 inch is 2.54 centimeters. Okay, so that's good. So now we're at centimeters. Now we can go directly from centimeters to meters, right? Okay, so I'm running out of colors here. I have to recycle. So we want centimeters on the bottom, so those cancel. Meters on the top. 1 meter is how many centimeters? 100. Okay, and so now we are thankfully halfway there, right? The meters, we got meters on the top. Now all we've got to do is get seconds on the bottom. We started with hours. Well, we could maybe do this in one step. Do you know how many seconds are there in an hour? 3,600. If you didn't remember that, or if you were, taking a SAT test and panicking, we'll just do it in 2 steps. We could just say, we've got hours need to cancel, right? And so we could go from hours to minutes if we wanted to, right? We could make that a minute. 1 hour is 60 minutes, right? And I got to stretch clear down here now. Times. Let's see, what are we going to do? How about gray? We haven't had gray in a long time. Okay, so now we've got minutes on the bottom. We want to cancel the minutes, top and bottom, and get seconds, right? 1 minute is 60 seconds, and we're there. Finally, we're there. Now we've got seconds on the bottom, right? All we'd have to do, 10 more seconds, all we'd have to do then is just multiply this times this times this times this, divided by whatever we get on the bottom, which is, 100 times 60 times 60, right? That's our number part. The unit's already worked out, meters per second. See how that works? Okay, that's a lot of stuff. All right.